Hello, can you hear me? Thank you. Thank you very much. Okie doke. How was your week? Basically, we talked this week about section 7.6, right? Oh, good. I'm glad. So, why don't we, where did 7.6 go? One in the right section would be useful. Sorry, my last session just went a little long, so I'm just a little frazzled. Okie doke. So 7.6, we're talking expected values. Let's just do a couple practice problems to make sure that we are working through this okay. Let's just start with number one. True or false? Sometimes the expected value is a negative number. What are we thinking? True. Why is that the case? Or rather, where does that being a negative number stem from? True. So in principle here, kind of what I was thinking about is that if our expected value is equal to our payoff times our probability, summed for all of our events, the fact that E could be negative stems from our payoff, not our probability. Because our probability is always going to be what? What's like a characteristic of the probability? All of our probabilities are going to be positive numbers that are less than 1. Because all of our probabilities summed together are going to be equal to 1. So all of the chances of our expected value being negative come from the possibility that the payoff may be negative, not the probability itself. Okie doke. Let's start simple and do problem number 4. Here we have a table giving us outcomes, E1 E2, E3, and E4. One sec, I just realized I didn't double check to make sure I was recording, and I am. Okay, sweet. Then we have our probabilities, which are 1/3, 1/6, 1/4, and 1/4. And then we have our payoff, which is 1, 0, 4, and -2. So if we remember, our expected value is equal to M1 P1 plus M2 P2 plus way up to Mn Pn. You can see where we have our payoffs and where we have our probabilities. And we can put these together to get our expected value, right? So we're going to end up with 1 times 1/3 plus 0 times 1/6 plus 4 plus -2. This is going to be 1/3 plus 0 plus 1 minus 1/2, which I'm going to turn into 3/6 plus 6/6. It's 2/6. 2/6 plus 6/6 minus 3/6. So that's 8/6 minus 3, which is 5. All right. No questions? That was basically just they gave us a table, they asked us to roll through it, and we did. Problem. Let's try a couple of these word problems. So this is a lot of just synthesizing information. We're going to start with number 7, I think. Mary will win $8 if she draws an ace from a set of 10 different cards from ace to 10. How much should she pay for one draw? Walk me through this. What is the first thing I should do? Okay. So here I have my probability, and here I have my payoff. I'm not going to label payoff, I'm just going to label M. So, yeah, this is going to turn out to be 80 cents. Can't remember the last time I used a cent symbol. So 80 cents is what we're paying for a reasonable price for this game. What about number 9? Again, same type of problem. David gets $12 if he throws a double on a single throw pair of die. How much should he pay for a throw? Well, we know what the payoff is going to be, right? Got that much. how are we going to define the probability? Yes. The probability is going to be the probability of rolling some number times the probability of rolling that number again. So this is going to be times 1 over 36, right? I'm not sure if that is right. So that's going to be rolling a number again. Seems reasonable to me, but that's not quite sitting right. Sorry, I'm sorry. It is a 6-sided dice. Single throw a double. That should be 1 over 6. Yep. So it should be 12 over 36, which comes out to be 1 over 36. Okay. Let's do number 13. I think this is a little bit more of a meaty problem. We have a fair coin that is being tossed 3 times. A player will win $3 if 3 tails occur, $2 if 2 tails occur, and loses $3 if no tails occur. If 1 tail occurs, nobody wins. So we're going to establish what the expected value of the game is. We're going to establish, is the game fair? And if the answer to that is no, then we should ask, how much should a player win or lose for a toss of exactly 1 tail to make the game fair? So let's start by breaking this up into what sample space exists. Like, what are the events that we can have? Our first step to solving these types of problems is to partition our sample space. So our sample space is going to be, yes, we have 3 tails. We have 2 tails. Rather, yes. How many times? Yes, we're tossing this coin 3 times. We are saying that order does matter because there are 3 different ways that we could achieve 2 tails being hit, right? Then 2 tails, then we have 1 tail. And then we have no tails. Did I miss any events? 3 tails, 2 tails, 1 tail, no tails. So rather, we're going to call this A1, and then all of these 2 tails, call that actually A3. This can be A2, A1, and A not. So we've established what our events are. Next, we need to determine what the probability is going to be. So we have 2, 3, 8 total types of events. Thus, what will my probabilities be? Yep. Then for 2. Yep. And so on. And so forth. Next, we need to return to our problem to determine what our payoff is going to be for each of these. For 3 tails, I am looking at $3. For 2, $2. 0 for 1. And what am I looking at for here? For 0 tails, my payoff is going to be -3. Exactly. So now our next section of the question is going to be, what is our expected value? We can calculate our expected value fairly easily by multiplying the payoffs and the probabilities of each of these events, as we did just a little bit earlier. So we're going to end up with 3/8 plus 6/8 plus 0 minus 3/8. So we end up with 3/8 minus 3/8, 6/8 is equal to 3/4. So our expected value is 3/4, or because in this case we're working with money, we're going to think about this as 75 cents. So, is this game fair? Nope. What could we do to make this game fair? First of all, who is it in favor of? It's in favor of the player, exactly. So how could we fix this game so that it would be totally fair? Any ideas? Yes, we would need to balance the equation. What could you suggest to do that? How could we add an additional minus 3/4 to this equation? Exactly. Exactly. So to balance the equation, we would need to turn this 0 into a -2 so that E would equal 0. And we would have a fair game. Awesome. Okay, any questions? Awesome. Let's try to do number 15. So this is, in the same line of the stuff that we've been doing, but just a little bit different. Here we have two sports teams that have played each other 14 times. Team A won 9 games and Team B won 5 games. They will play again next week. Bob offers to bet $6 on Team A, while you bet $4 on Team B, and the winner gets $10. Is the bet fair to you in view of the past records of the two teams? How are we going to set this up? Because here it's not so clear about what necessarily the payoff is immediately and what necessarily the probabilities are. So how would you go about setting this up? Team A is 9. Yep. So we're looking at probabilities right now. Our probability is going to be 9 out of 14 chances that they win. And then, yeah, Team B is over here hanging out at 5 over 14 chances that they win. So the event that A wins versus the event that B wins. Now, what about our payoffs? If Team A wins, what is your payoff? We're kind of thinking about it from the perspective of you. Yes. So here we have -4. You lose your $4. And here you're going to gain $6. So we can set this up as E is equal to -4 times 9 over 14 plus 6 times 5 over 14, which is going to turn out to be, I would put this into a calculator. I know you guys are not allowed to use calculators on exams, so perhaps I should not actually. I would just shove this into a calculator if you had the opportunity. But this is going to be -36 over 14 plus 30 over 14. So this turns into minus 6 over 14 or minus 3 over 7. Which now I'm just going to shove into a calculator because I don't really know what 3/7 is. So this is going to turn out to be minus 43. I'm pretty sure that they don't put calculators on exams as a general rule of the math department, but definitely check the syllabus for this class. I haven't really GSG'd for this class before, so I'm not entirely like up on the rules, but I'm pretty sure the math department generally doesn't like calculators on exams. But definitely check the syllabus because there's a chance that, you know, they just put one in and let you go, you roll with it. But I mean, obviously on an exam, they wouldn't expect you to know what 3/7 is. So you don't need to worry about that. They would probably ask you to know what 3/4 is, but you know what that is. So, is this bet fair to you in view of the past records of the two teams? No, exactly. So because our expected value is a negative number and, well, is the fact expected value is not 0, it's not fair generally speaking, but especially not fair to you because you are going to end up being the one losing out on this. Okie doke. Lost the question I wanted to do. It's 21. So let's do that. So here they give you a big old table. The following data give the number of new houses sold in thousands in the United States in 2009 for prices under $750,000. Oofda. Use the midpoint, which they give you, to find the expected sale price of a new house. So, the expected sale price of a new house. We have a series of events, houses that are divvied up into a variety of midpoints. We have houses that are divvied up into a variety of price brackets. We have the midpoint of each of these. What is that going to correspond to? So in order to find the expected value, we're going to need both the probability and the midpoint, or not the midpoint, and the expected payoff. What do we have? What information do we have, and what information do we have yet to put together? Yes, we need the number of homes sold, which we can do, our total number of homes. I think is 365. I should plug it into a calculator. So what can we use this information for? How do we get to put this together? Why do we want the total number of homes sold? Bingo. Okay, you got it. So we have the midpoint, which is going to correspond to our payoff. So for here, it's $75,000. I'm just using that K to represent thousands. $175,000. $250,000. $350,000. $450,000. And $625,000. And then we have our probabilities, which are going to be the number of homes sold divided by the total number of homes. So in this case, it's going to be 66 over 365. And then we have 96 over 365. We have 114 over 365. We have 46 over 365. And you can kind of see that the number begins to taper off the more expensive that they get, which does make sense, like logically speaking. We're going to sell more homes that are worth $250,000 as compared to $625,000. And then we can put this all together to get our expected value, the same method that we've done 100 times in this section. And this is pretty rough, and this is the problem that you would definitely want to use a calculator with. So I'm going to have to plug it into a calculator. So this is going to be 13,561 for M1P1, or rather 62. I don't know if you have a calculator with you, if you can help me out real quick, just to save a little bit of time. And as expected, as our probability begins to taper off, the amount it's contributing to our expected value is also going to begin to taper off. So that's going to be so then I'm going to go back and add all of these up. This is going to turn out to be $246,438. Does this make sense? Is this a reasonable answer to get for the expected sale price of a new house? And how can we tell? It's not too dramatic. We know which houses sold with the most probability and we expect that our expected value is going to be somewhere in that nearness. And so the fact that it's pretty close to $250,000, which is what almost half of the houses sold for, no, a little less than half, a good portion of them sold for. I think it's a reasonable answer to get. Okie doke. Let us do problem 27. So here we have site selection. This is, again, a little bit different of a take on this type of problem. We have a company operating a chain of supermarkets, and it plans to open a new store in either one or in one of two locations. So it's an either or. It conducted a survey of the two locations and estimated that the first location will show an annual profit of $15,000 if successful and a $3,000 loss otherwise. For the second location, the estimated annual profit is $20,000 if successful and a $6,000 loss otherwise. So if the probability of success in each location is 1/2, what location should the management decide on in order to maximize its expected profit? So basically what we're going to do here is we're going to compare what the expected profit is at location 1 and location 2. How am I going to set this up? I'm going to start with location 1. What is this expected profit going to be at this location? Yes, precisely. So we have $15,000, which is our expected profit if we succeed, times the probability we succeed minus, essentially, plus a negative number. $3,000 times the chances that we fail. So exactly, this is going to turn out to be $6,000. Now let's compare to our second store. Same setup, $20,000 for success, half a chance of success, $6,000 for a failure, half a chance of failure. Expected value here is 10,000 minus 3,000. It's going to be $7,000. So, what location should the management pick? Location 2. It has a larger expected profit. How do you think this is going to change when we change the probability of success? In part 2 of this problem, yes. So we're changing the probability of success, and my hypothesis, based on how much the probability of success is changing, is that it is going to be altered in favor of the first location based upon the magnitude of change. So this is going to end up being $10,000 minus $1,000, which is 9,000 expected, and this is going to be less than 7,000. It is going to be $6,666 minus 4,000. right? So that's like 6,600 minus 4,000, which is going to be 2,666 dollars. So again, as we expected, we are going to select location 1 because it has a greater expected value. And up here, when the chances are 1/2, we're going to be selecting location 2 because it has a greater expected value. Any questions, comments, or concerns? I can double check the syllabus to make sure that you guys can or cannot use a calculator, and I can email you actually once I double check that. Sorry to give you the heebie-jeebies if I'm wrong, so I will double check that. Otherwise, this is basically all I've got. I don't think so. I don't think that I have access to that. Or rather, I think I do have access, but it gets scrambled every time. So I can like see problems, but not all of them at the same time. Let me check that. Okay. My guess is that they get scrambled. Do you know which question it was? Ticket A and B. Oh, you have received 2 speeding tickets. Ticket A is for $100 and ticket B is for $150. Oh, sweet. And yes, it is. Let me change this so that there is space. So you have received 2 speeding tickets. Ticket A is for $100 and ticket B is for $150. You weren't clear about probabilities. You're going to the court to try to get out of one or both of the tickets. The probability of getting out of ticket A is 0.4. So the way that I read that is 0.4, you get out. This is for A. And 0.6, you don't. And then for B, the chances are 0.2 you get out and 0.8 that you don't. Calculate the expected value, or rather the expected amount that you'll have to pay out for tickets. So the way that I would approach this problem is to say I have an expected value, which is equal to the probability that I pay out for a ticket versus the probability that I don't pay out for it, or rather, the probability that I pay out for a ticket times the amount I will have to pay out. Is this kind of how you approached it? Because I would set it up like this. I would say my first payout for ticket A, which I'm going to do in blue, I guess. I'm going to call that, I am going to pay $100 if I can't get out of it. Then I have ticket B, which is going to cost me $150 if I can't get out of it. So I would say that this is going to be equal to 60 plus 150 times 0.8, which is 4/5. So that's 120. Now that's fine. So I would say that your expected value is going to be 180. Right? Because, yeah, for sure. Because the idea is that there is a chance that you get out of these tickets. The expected value is not the full $250 that you owe on the tickets. The expected value is less than that. But I would break it up into what is the probability you get out of this ticket versus what is the probability that you don't. Additionally, if you just wanted to throw in, you could include the sections here. For instance, here is the probability that you get out of the ticket. That's going to be $0 that you pay times 0.4. And here is the probability that you get out of this ticket, which is $0 times 0.2. And the reason we don't need to include those is because obviously they're going to zero out. So that's why we're not like including the probability that you get out. It's really the probability that you don't get out, because that's what's going to cause an expected value. Okay. Thank you for coming. Do you have any other questions, comments, or concerns with this material? If not, then I hope you have a great evening and a great weekend. Thank you so much for dropping by. Have a good one.